Hi, this is Olivia with my video presentation for Physics 111. I chose a problem from the second unit exam, question 3, part D, which related to the unit goal of being able to use integration to determine the electric field due to a finite length line. So the question says, set up but do not evaluate the integral for this scenario. Be sure to specify integration limits and expressions of values for dq and r. So this is a uniformly charged rod that's 60 centimeters long. 5 centimeters from the rod is x, which is the spot where we want to find the electric field. And it's also given that lambda equals 0.4 microcoulombs per meter. So before we start the problem, it's important to note that you cannot use Gauss's law for this question. There's two criteria to use Gauss's law. The first is that the magnitude of the electric field is constant everywhere on the Gaussian surface, and the second is anywhere that the electric field crosses the Gaussian surface, it does so perpendicular to the surface. And in this question, the electric field at the end of the rod is not constant, and also x is not perpendicular to the rod. So in other words, this problem can only be solved by integrating. When I saw this problem on the test, I wrote down E equals k, the integral of k over r squared dq. I knew this is the equation we were supposed to use, but besides that, I wasn't really sure what to do. I remember we had done an example in class where we had little l's and big L's and d's, and we had to find the limits of integration, and I was kind of confused, so I just skipped the problem. So the main question is, how exactly do we go about solving a question like this? The first thing we have to figure out is, what is dq? dq is the amount of charge on one little piece of the segment, in this case the rod. In other words, it's the charge density times the integration element. And we know that for a rod, dq equals q over L, or length, times dl, which you can also rewrite as lambda dl. Now that we know what dq is, we can rewrite the integral as E, or the electric field, equals the integral of k times lambda over r squared dl, where k is a constant, lambda is the charge per unit length, and r is the distance of the charge element to x. Going back to the original picture, I changed everything from centimeters to meters, and then I chose two little l values. On the far right, I said that L equals 0.05 meters, because that's how far away it is from x, based on the d value, which is 0.05. And then on the far left, I said that little l equals 0.65 meters, and that simply comes from adding the big L, which is 0.6, plus the little l, which is 0.05, to equal 0.65 meters. So when we integrate, we want to integrate from the beginning of the rod to the end of the rod. So the limits of integration will be 0.05 to 0.65. The integral now looks like this. So the last part we have to do is figure out what r is. Now the goal is to rewrite r in terms of little l, so that when we plug in the limits of integration, we get the distances we just figured out in the last slide. And those distances were 0.05 and 0.6, which are the same exact things as the limits of integration, so we can just simply plug in L for R. The final answer is E equals the integral from 0.05 to 0.6 k lambda over L squared dl. Now you might be thinking, well, is this the only way that you can solve this question? And the answer is no. There's a lot of different ways you can go about solving this question depending on what you choose little l to be. For example, let's say you look at this problem and you decide, well, I want the left side to equal 0, so little l will equal 0, and I want the right side to be the length of the rod, or L, which is 0.6 meters. The equation will stay the same, E equals the integral of k lambda over r squared dl, The limits of integration will change based on the L values you chose in the previous slide. So instead of going from 0.05 to 0.65, it will go from 0 to 0.6. Now the tricky part is the R value. Instead of R just being replaced by L, it's replaced by big L plus D minus little l. This might seem really complicated, but it actually makes sense, because remember, we want to plug in the limits of integration into little l in order to find the distance the rod is from x at that particular point. So when we plug in 0.6 for L, 0.05 for D, which were just given in the original question, we can plug in the lower limit of integration, 0, for little l, and we get 0.65 meters, which if you look at the picture, when L is 0, it is 0.65 meters away from x. Likewise, if we do the same for the upper limit, 0.6, we'll get 0.05 meters. And if you look at the far right side of the rod, it is 0.05 meters away from x at that point. The final equation is E equals the integral from 0 to 0.60 of k lambda over L plus d minus L quantity squared dl.